Welcome. My objective today in this brief overview is to give you an idea of the nature of the key components of the computer systems that we use. And I'll be really at three levels. Level one, we'll be looking at the hardware, the devices that make up the computer system. Level two will be at the level of software, the programs that make systems do useful things. And the third level will be about applications, which are the kinds of programs that you actually use in practice in whatever type of area in which you work. So the three levels are, and I'll touch a bit on communications as well as I go through the hardware. So that should give you a pretty good overview. Now, in addition to this material, there will be other material that we'll make available, but the idea here is a quick and dirty overview of these kind of basic areas. I'd like to start this by saying that in many ways, still talking about these devices is obsolete. We've come to a point now where we've recognized that the technologies that we have, the computers, have hardware-wise everything that we really need, although every year it gets better and new devices, which I'll talk about, come out. But by and large, the hardware part of the system really doesn't impact what we do very much anymore. It used to be that it was a big deal, but now it isn't. Far more important is the upper layer. In fact, it isn't even important to know much about software itself and how it works. It's really the upper layer, the applications layer, the applications that run on the computer that are issues. In other words, to get good programs that allow me to do the real things I want to do. And more than any of that is all of the factors that we need to address that surround the computer system. That total set of factors is really crucial. So we recognize that computer systems really work in a human context. People must use them. People are affected by them. Patients are affected by them. They interfere with some of the things we do. They help other things that we do. So there are many, many what I usually call psychosocial and organizational issues that surround the computer system. They're far more important to understand than the things we'll talk about today. But it's sort of a characteristic of all of us that unless we understand a little bit about the stuff we're using, we kind of feel uncomfortable. We kind of feel that we don't really understand what we're doing. And unfortunately, it blocks people in what they need to accomplish. So what I'll do in going through this is kind of relieve that distress. And I take it about only that seriously, a relieving of distress. I'm not intending here to give you a scientific view of computer systems. I am not intending here to be absolutely complete. I am not intending here to turn you into someone that can write a program or understand or even put together hardware. I just want to give a broad understanding of the hardware, the software, and the applications that make up computer systems. And I think you'll find that this is sufficient. If you come to a point after hearing this that you want more detail, your best bet is to go to the web, look up different aspects of systems, and study them online. That's the easiest, cheapest, and quickest way to get that kind of information, particularly related to new types of things that happen from now on or that I don't mention. The only way you'll find out about them is in the area of books or the web, or even talking to other people. There are also some good programs on television. There's a regular program on one of the community access channels that I have seen in several cities now. It, I believe, is broadcast from Vancouver, and what it does is talk about all kinds of hardware devices. Almost certainly there is an online archive of all those shows. It's been going on for at least 8 or 9 years, maybe more. So you can find this kind of thing also on the web in the organization's archives that put on this type of show, that let people know about hardware and software and things that are important for work. And that stuff will be general stuff, not related to health information management or health informatics. So the very basic concept that we start with is the concept of a system. And I'll draw some things on the board. Mainly, the purpose of the board is to focus my own attention. If you think about the concept of a system, it's very simple. There is a set of inputs to the system. So inputs, these are the things that go into a system. The system, by the way, could be a computer or it could be a human process. It does not have to be a computer. There ultimately come out of the processor here, the system, some sorts of outputs, and I'll give you examples of those. The system tends to store information, so there's usually some sort of storage to hold information for periods of time. There is here a system processor of some kind. It could be a bunch of humans or a computer, so there's a processor, P-R-O-C-E-S-S-O-R. And there are devices that, as you call input devices and output devices, that are connected to the system by communications lines. And one could view any of these lines I've drawn as communications lines. This is very high-speed communications for storing information and getting it back. This is perhaps lower speed information for inputs because humans are slow inputters. But you could have, of course, input from another computer and outputs. And there are lines that connect the devices that attach to this system, very simply attached to this system through these communications devices, which today tends to be the Internet. In other words, the way I connect to a remote computer is through the Internet. If I have a local computer, like this is just an open box of one sitting here, I connect to it with a wire that goes into the computer. In some computers, for example, if I have for this box an input device, it will be a physically separate keyboard that I can type on, which is connected by wire into the box. And but if I have a laptop, the keyboard is integrated into the system. So when I hit the key here, it goes directly into the processor, which is built into the back of the laptop, and comes out on the output screen, which is part of the laptop. So computer systems can be fully integrated configurations with all of their inputs and processors and output devices in there, typical of a laptop, or they can have their input-output devices attached to them by wires. And either of these types of computers can be connected through some sort of a line to the Internet to communicate with other computers located elsewhere. So the communications devices are the way of moving data outside. Let's take each of these one at a time. All right. I've already mentioned one type of input device, the keyboard. The keyboard has been around for a long time. The idea here is humans type. The keyboard is arranged typically, although there are variations, just the same as a typewriter keyboard, which is kind of silly because typewriter keyboards were actually designed to prevent the old mechanical mechanisms from jamming if people type too fast. We use it now because it's familiar, although you see in industrial applications sometimes a keyboard organized alphabetically, or we have other types of keyboards, none of which have ever become very popular. So the QWERTY keyboard, as it's called, going for the letters on the first line of letters, QWERTY, is a typical keyboard. But there are many, many other kinds of input devices. You've seen, I'm sure, and are familiar with the mouse. The mouse is a device which you can move around on some surface or in space. There are three-dimensional mice that allow you to move the thing in 3 dimensions, and that information goes into the computer. And what the mouse does is send to the processor information about where it is. So I am here on the table, and you just move me 3 inches down and to the right. That information about the position of the mouse is developed within the mouse with little wheels or optical devices and sent to the computer. So it's a positioning device. It puts onto the screen a position. There are variations of the mouse. There are trackballs, which used to be very popular. Instead of moving the mouse around what you do is roll this, move your finger on this little ball, which does the same thing. It moves a cursor around the screen, and you're able to use that to point. People who have laptops realize they've got these little things here, the IBM type device, which allows you to put pressure one way or the other way, horizontally or vertically, and it moves the cursor around the screen. So many kinds of positioning devices. So a keyboard is for entering in textual information. A mouse is for individual characters for the keyboard. A mouse for positioning yourself in a space, like on a screen. There are other input devices. There are voice type devices. These are devices that change human sound, which is a simple signal. By breaking it up and giving it a numeric value for the loudness of the sound in time, we end up getting a waveform, for example, as the sound looks something like that. And there are ways of getting that voice or sound information into the processor. And just to go a little bit forward, in the case of voice type information, there may be an applications program running on this computer which is able to turn this bunch of squiggles, which is actually in the computer in the form of a bunch of discrete levels like this, turn that into words that you speak. So it's able to recognize from the variation in the waveform, digital waveform, there's separate little measurements there, it's able to recognize the words that you speak. So an area is usually called speech recognition, which is the ability to use a voice type input device so that what you say can be recognized. And just a little confusion is with voice recognition, that's really a security type mechanism which allows someone's voice to be recognized as that person. So it's another way of verifying who I am when I'm attempting to use a computer system. So there are voice type devices. There are all sorts of signal devices, signal type, and really voice is an example of that. But in the case of signal devices, I could, for example, put wires attached to my forehead, and I can use that as or device attached to my forehead. As I move my head, it can move a cursor around the screen. It could be a positioning device. So I can use signals to position. I can use devices that take light and reflect it off my eyeball, go back into a device which figures out what I'm looking at, and it's called eye tracking, and I can use that as positioning type device. There also is, and there are many variations here, the possibility of mass input, I'll call it. And this is where I have already created a document or a bunch of letters and numbers that correspond to a text. And that text is already somewhere else in a file. It's usually called, it's not just stored somewhere. And what I'm doing in that case is moving that data through a communications line and making it input to the processor. So I can download a file from the internet, which means I'm taking a bunch of information that existed out on the internet somewhere, and I'm running it through the internet into my computer, and that is an input of documents. It could be an input of pictures. An example of that would be in the case of radiological images, which would be picture archiving and communication systems. So I can have many, many kinds of input. And usually this is called multimedia input, meaning different media. An example of a medium would be keyboard. Another example would be a picture, an image. Another example could be a signal. And anything you can think of can be brought into a computer. Signal type, I could, for example, put leads on your chest and bring your electrocardiographic information in the same way I can bring the voice in. So the electrocardiographic information would be coming in. It looks a signal sort of like this, and I simply turn that by a process called digital sampling. I turn it into a series of numbers that indicate the height of the waveform at each point. So I can take your electrocardiogram and get it into the computer and be able to recognize if it's as some pathology, for example. If there's a problem with your heart that's indicated by the shape or the timing of the waves in that electrocardiogram. I can do that with electroencephalography as well. I can take brain waves and put them in. And just to show you how far it's going, at the University of Waterloo, the electrical engineering department is in the process of building a laboratory which is called a human-machine interface laboratory, and as part of it is called brain computing. In this instance, what we're doing is taking signals from the brain and recognizing what a person is thinking about, and then through the processor recognizing it, and then being able to, for example, control an airplane or to control an arm when the person is unable to move. And you may have seen some of this type of work on television. Recently, they showed a monkey that was able to move a remote mechanical arm through simple thinking and be able to pick up a banana and deliver it with this mechanical arm to his cage. So that's examples, a set of examples of input devices. This to the other side here, it would do us no good to pour stuff into this system and store it. I mean, we want to see it sometime in some form. For example, we might want to hear the voice or learn the diagnosis of the electrocardiogram, hear the voice of the radiologist or recognize the electrocardiogram and be able to diagnose it. So different output devices. The common one is the screen, and there are many types. This is called a liquid crystal screen. It doesn't really matter what the technology is. It's simply a way of painting human readable information or human viewable information onto a two-dimensional surface and being able to allow us to read it. And of course, it doesn't have to be a two-dimensional surface. Today we have many game systems that have three-dimensional capabilities, and usually you have to wear a special headset, which is the output device, and has screens for each eye and delivers a slightly different image to each eye, which corresponds to the stereoscopic separation that occurs in real life. And then I see the object or the picture in 3 dimensions. So the typical output device is the screen of many, many kinds. I'll put over here screens. These can be liquid crystal, they can be plasma, they can be cathode ray tube, the old television-like systems. They're all the same basically in what they do, they work different ways. We also have the potential of sound. So if I recorded my voice, I could hear it on output. So I could check to see if my voice was recorded. This thing that's being done here right now, what we're involved in, involves taking sound from my voice and running it into a computer system, which turns it into numbers. And then if later on it's played back through a computer system where you can hear it. And of course, we're all used to sound now because we have music and so on. So sound can be there. The screens, by the way, can have text. There's like letters and numbers. I can have pictures of various kinds, and they can be two-dimensional or three-dimensional, or it's called four-dimensional, which means they can be motion pictures, the equivalent of video, which introduces the fourth dimension of time. There are many other possibilities in terms of the different types of output. I, for example, can have a printer, and there are many, many types of printers. Some are fast, some are slow. Some spray little dots onto the piece of paper. Others put information onto the paper using a process that puts charges the paper electrostatically and then coats it with very fine carbon particles that is then developed inside the system, stuck to the paper, and that's a laser printer. So you have inkjet printers, laser printers, and you can have plotters, many devices which allow you to take, for example, signals like this and plot them one on top of another. You can put that out on paper using a variety of technologies. So many, many devices are available for output. And I guess what you get out of this is one of the real innovational areas in the world of computer systems is this type of these sets of devices. For example, you might come up with a completely new approach instead of a keyboard for entering textual information. One example, instead of typing things, you might select things on a screen from a list. So pull-down menus are a variation in the use of a keyboard because it allows you to use pointing type devices like a mouse to, in fact, put into the processor a selection from a list, which instead of typing it. So, but there's a continuous improvement in the types of input devices and a continuous improvement in the types of output devices. And also, with time, each of these becomes less and less and less expensive. So the cost of doing input and output from a device's vantage point becomes less and less. Now, in saying that, at the same time, I need to recognize that the cost of the human doing it goes up and up, unless we find some way to get information from a human more quickly. A human still has to sit there and dictate a report. It's a human-intensive process, and none of these devices improves it. Some can slow it down, like the use of the keyboard. Others may seem to speed it up, such as the use of speech recognition. Certainly moving radiographs through a computer and bringing them in is faster than moving films around. So you have to really look at the whole picture. Even though these devices get to be dirt cheap, there still are issues related to the human side of the equation. Similarly, with output devices, there's constant innovation. New types of devices are created. They tend to become cheaper and cheaper. What's interesting, and I'm sure you've seen this on the market, is if you today buy a printer, an inkjet printer, the cost of that printer has gotten to be so low that it's crazy. And usually today, you don't just buy the printer. Usually it includes, all in one box, a printer, an optical scanner that lets you turn documents into pictures that the computer can deal with, or even recognize the type on the page. It includes a fax machine capability usually, and it may even include other capabilities. These combination devices exist that are cheaper than the cheapest computer output device was a few years ago. So the devices are becoming literally dirt cheap in many cases, including fancy color and beautiful pictures and photographic quality and all of that. But the ink is still an extremely expensive commodity. And of course the manufacturers sell the devices, but where they really make their money is from the supplies that they provide, cartridges for laser printers, ink, little whatever you call those plastic things that go into the inkjet printer. Very expensive. So expensive that you may get advised when you go to buy a replacement set of ink cartridges, it'll be cheaper to repurchase the computer than to do buy the cartridges in some cases. So very interesting how even though devices become cheap, there still needs to be ways in which, that in the case of output devices, the companies make money. And really what it is in these consumables that money is made. So that's the output device world. Now, the processor here basically takes information in and does something with it. And you're probably aware a little bit about this, that just to give you a few points without getting very deep into it, is that computers can only process the equivalent of numeric information. So if I type an A on a keyboard, a certain set of codes goes in. I can't remember the exact code, but something like this goes into the computer. So it's 110000. That's what happens. The keyboard contains electronics that when you hit the A key, it sends a code in called the ASCII code in, and that code is what actually goes into the processor. So what goes into the memory of the computer, and I'll talk about memory in 1 second, is this code, not the letter A. It's a code for the letter A. And interestingly enough, this code also could be a number. It could be the a number of whatever it comes out to be of certainly a few hundred, where that number is represented in what's called binary arithmetic, where digits can be 0 or 1. In decimal arithmetic, they can be 0 to 9. In binary, they can be 0 to 1. And it's a lot simpler to make computational devices in the processor that deal with these zeros and ones as a two digits rather than 0 to 9. And if you're curious, back in the 60s, there were computers that worked on the decimal system and internally dealt with decimal arithmetic. They've disappeared. What we do is use this type of binary system. So one weird thing is that computers only deal with these numeric representations of the world, either letters or numbers or a picture. Give you an example of a picture. If you had a number like this, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. Well, then you've got a line here. In fact, if I do this other one, it'll be even more clear. That's the equivalent of vertical line in a two-dimensional picture. That would tell me that there's to be a line down that picture. So I can use this numeric information to create a picture in a number of different ways. That's an extremely simplistic view of it. That type of information is what we deal with. When information is brought into the processor, and this is not important really, although when you buy a computer it can be important, there really is something in the computer called internal memory. And what this is memory on which the processor can work. So it's a temporary place. I think about it sort of like a desktop, a temporary place in the computer where I can do my arithmetic. So I put the number into this. Let's make the memory over here like this. I put into one memory location, and I'll do this in decimal to make it simple. I put into memory location a 3, and the next location I put a 4. And what I can tell the processor to do is go to location number 1, this is location number 2, take the number that's in location number 1, and put it into your adder, your place where you add things, and take the location number in location 2 and put it into your adder, and then add the two of them together and put the result in location 3. So 3 plus 4 is 7 in location 3. That's basically what computers do when they work with arithmetic. So there are pieces of hardware that help to do various kinds of arithmetic. They can compare these numeric representations. They can calculate, like multiply or add. Some of them do it by very strange methods that we wouldn't use as humans. We have quicker ways of doing it for humans, but for computers, they can do so many more per second that it's actually easier to use other methods to do, for example, additions or multiplications. So this is basically what happens. The memory of the computer is where things are stored while the processor works on them. The storage, which is usually in the form of disks, and these can be very, very large, tape, which is still used in a number of environments, typically cartridge tape, and other devices. There are new solid-state devices, for example. You may be familiar with the hardware in a memory stick, that you have these little memory sticks that you can hold things. This is actually a different kind of memory, and we can put storage now made of electronic storage is the best term for it. So a type of electronic storage, while these are really magnetic storage devices. Again, none of this really matters in terms of what you really need to know. So what could be done in a processor is I put in number 3, it goes into a memory location, I put in the number 4, and I command the processor to add those. I get the result 7, and it's all in memory, and I say, okay, save that for later use, and I put the 7 somewhere out on storage in the disk. And of course, this would not be, it would be huge numbers and large numbers of numbers that would go into the memory devices. So the internal memory of the computer is where the computer works on stuff. Here it's put like on a shelf. So I usually think of these like file cabinets or shelves. Shelves is also good. It's a place to put things on I'm not working with them right now. They're there for later. I can use them when I need them. I can go get the result and see what it was. What was the result I got yesterday? Well, I can go and hopefully it's indexed by when it was done. Well, I got 7. And I can bring that back into the memory, and I could print it out on the output device. So I take the numbers in, I add them, work on them within the internal memory of the computer. When I'm done, I store it on the disk or other devices, and then later on I output it to the screen so I can see it, what number I got yesterday. And of course, you're probably familiar with things like spreadsheets that take whole arrays of numbers and do all of these things with them. So when we buy a computer system, we're concerned about the speed of the processor. The power is probably a better word, because there are many kinds of processors. So instead of speed, I'd say the power of the processor. This is how quickly it can carry out functions using whatever internal processing devices it has. And today, those are very, very complex. In fact, in today's laptops even, we have processor devices with really several cores, they call it, several separate processors built in. 2, 4 of them, even more, can be built in. And we've got faster and faster electronics, more and more electronics on a square inch, so that we're able to do incredible amounts of computation. And in fact, these are so powerful that we need good cooling systems, because the electronics heats up, and that becomes a problem. So the internal, this is power, so we get a Pentium or a Mac, and it's got certain characteristics, and I don't even keep up with that anymore. I used to know that stuff cold because I did a lot of consulting, but the truth is you need to go out, compare systems, look at magazines, look online, and see which of the computers is fast enough to do what you need to do. And most of us don't really require computers that are very fast at all. So we can buy less expensive laptops. The exceptions would be if you're going to get big into games. Some of the games require very sophisticated, very high-speed processors to be able to handle the display and motion making that they do. So one aspect is the power of the computer processor. Another aspect is the amount of memory and speed of this, amount and speed of the memory. And today you're probably aware that memory is measured in billions of bytes, billions of these. This is a byte, billions of bytes. So you'll see a term, you probably have heard the term megabyte. Megabyte. That means, it's usually BYTE, by the way. Megabyte, that means a million. So it's a million. 1 and 6 zeros, 1 by 10 to the 6. It means a 1 followed by 6 zeros. And the next level up is gigabyte, which is 1 with 10 to the 9, which 9 zeros, a 1 followed by 9 zeros. And then after that is terabyte, where I just went out and I bought a disk as a backup disk for my computer, and it's 1 terabyte, which is another 3, 10 to the 12th. So it's a million megabytes. Unbelievable amount of memory. You can buy, in my case, I bought it for a very inexpensive amount of money. I'm sure next year it'll be even cheaper, much cheaper. So the internal memory of computers today tends to be in the range of gigabytes, 2, 3, 4, 8 for laptops, perhaps a bit more for some of the desktop type machines. The used to be, when you bought a computer, it was in the megabyte level, so it's gone up by 1,000 in only about, I'd say, 6 years. It will not be long before we'll be talking in the hundreds of gigabytes or terabytes of internal memory, meaning we put huge amounts of information that the processor can deal with. Gigantic pictures, whole libraries of information can be put right into the memory so it can be quickly worked on. In addition, the storage devices are today measured beyond the gigabyte range, typically out to the gigaterabytes. So I bought that backup disk, 1 terabyte, 1 trillion bytes of information, which is a huge amount. But today we've got computers that go up even higher than that, 1,000 times that. So what's happening in, I guess the picture here is, There are more and more kinds of input devices with more and more flexibility allowed by them to get information into the processor. There are more and more output devices to get information out in beautiful forms and quickly. There are more and more powerful processors that allow me to compute things very quickly. Bigger and bigger internal memories that allow me to hold more information right with the processor so I can quickly access it, typically in millionths of a second or even better. And gigantic storage devices that allow me to hold everything that I do without worrying about how much space it takes up, to the extent today that this has become storage devices and so on fill up whole acres of land in some of the major companies like Google and Microsoft and places like that. So the advances that occur in the storage are the amount of storage that can be stored in a given volume. It used to be that if you wanted to store 1 megabyte, it would take the whole floor of this building, as back in the 40s and 50s. Today, if you want to store a megabyte, or if you want to store, in fact, in the case of my memory key, this one here is 16 gigabytes, and it fits in much less than a cubic inch. The volume in which it's stored constantly goes down. Second thing that happens, the quickness with which I can put it onto the device and get it off again keeps going up. So I'm able to move information between this external storage and the internal memory very, very quickly, and we get faster and faster with that. Very interesting aspect of the way systems evolve, and this does talk a lot about evolution. Now, just to mention a few things that related to this, I've mentioned that input devices constantly evolve, output devices constantly evolve, and how these other aspects evolve. But beyond the size of the devices, there are new strategies that are very interesting. I'll give you one of them. One of the types of storage device that you can have on outside here is called a RAID device, R-A-I-D. It means that a redundant array of independent disks. So what it is a cabinet filled with disk drives. I'm just looking at them edge on here. A whole bunch of them, typically 4 or 5 or more, each of which can be any size into the terabytes certainly range. And what's done here, because we've got plenty of space now, is if I put information onto disk A here, and some onto B and some onto C. If I copy some of, let's say, the C information in such a way that some of it is also on here, and the A information is also on here, and so on, I can cross-copy all the information in these different disks in such a way, and with other other information added as well, that if I took this B drive out of the disk array and destroyed it, broke it on the ground, and then I put in another blank disk, that all of the information that was on B, which is redundantly arranged throughout this array, would be reconstructed. So I can completely reconstruct what was there. It's a fantastic. It's called a RAID 5. It's a level 5 type. There's simple things like making just a simple copy from one disk to another, and that's RAID 1. So you go up the chain if you want. RAID 5 is where I can completely reconstruct disk B from the information on the other disks. Let's go one step further. Instead of having these disks in one location, let's have a RAID 5 array here, and then over in Vancouver we have another RAID 5 array, and down in Denver we've got another RAID 5 array, and over in Toronto we've got another RAID 5 array. And let's do the same thing that we did with each of these individual disks across that space, so that I copy some of Denver's records to Toronto, to Vancouver and wherever else. I copy Toronto's to Vancouver and Denver. So I do the same kind of thing, and I keep information on how I've done this. So it's called metadata, which directs me to what I've done. What's interesting now is if I had a fire in one of these locations, let's say in the Toronto location, if I have a fire that completely destroys all the disk, if this was just a RAID 5 array, and let's say it was destroyed, it would be gone. There's nothing to reconstruct it from. But if over in Denver and Vancouver and wherever else, I've got the information, I'm able to completely reconstruct this particular location. So now I've got absolute redundancy in my system, which protects me from natural disasters, protects me from fires, deliberate destruction by employees, whatever it might be. So there are strategies that can be used in how we place devices, for example, like storage devices, and how we arrange them and how we manage the information across them. There's a company in Canada called Bycast, B-Y-C-A-S-T, that does this, and it's, I believe, IBM, Hewlett-Packard, and other companies resell their product. So it's an example of this. That happens to be a built-in Canada, the company's in Vancouver, solution. And they're probably competing ones as well. But what this means today and what it's used for now is if I have image information, this is related to cancer patients, I can have it distributed around. Of course, it can be encrypted. It would be encrypted. But distributed around using this approach or formula, if you want, or algorithm for storage, and it completely protects any one location from losing all of its information. And of course, the more of these we have, the more locations it can protect. So if there was a disaster that encompassed all the facilities in the Vancouver region, then I could reconstruct that from the data and metadata that was kept at these other locations. You'll see all kinds of things about this. There's things called storage networks, SAN storage array. I can't remember what that stands for anymore, but the arrays of disks set up in such a way that at one location you've got a copy, another location you've got a copy, and you're able to deal with this quite storage area network, I believe it's called. Anyway, that is one type of thing that can be done. Similarly, related to the input devices, I could have, for example, input in multiple locations. So if one gets knocked out due to an electric storm or flood, other places can do it. They just simply are able to share the information and get it into the computer. I can have, of course, backup output devices wherever they're needed, so I could be able to bring them in and replace it very quickly. So today we're getting towards the point where our hardware systems are becoming very reliable and able to survive some of these disasters that occur in very, very interesting ways. So that's a quick overview of the major aspects of hardware. And you'll have an opportunity in the boot camp to ask questions. So if you want to, if you have particular questions or particular types of devices you're interested in, we can fill those in at our monthly question and answer sessions, and there's a blog that you can put your questions on as well. The one challenge might be to, next time you have a few minutes, look around in your location of work and try to identify all the different input devices, all the different output devices. Try to get some idea of where the processors are. And it can be very, very interesting. For example, there might be a processor built into something. You don't even know it's there. So you could have a processor built into a camera. In fact, many of our digital cameras today have computer processors built into them. You can have processors built into television. We can have processors built into even handheld devices. Another type of input device is what looks like an ordinary pen. And as you write on special paper, some of them require, others don't require special paper. Everything that you write is turned into numeric position information and stored in the pen. And then when you go back to your office, you plug that into a little device, and all that stuff is drained out. The information that's on there is recognized as the letters that you wrote or the numbers that you wrote. And so your pen contains the information and usually has a device in there to turn its position information into numbers and to store that information and maybe even do some pre-processing of that information. So it's very interesting and important. Storage devices can be in many locations, and I'll talk a little bit more about that in the future, but just one example of that, for example, is the use of storage devices in medical devices that are implanted. So you can have a pacemaker or other device that has that information that is stored in there and kept so that it can be read back by the physician. So that's an overview of hardware. I'll probably provide you with other information on this through a series of other recordings, but that's the basics. Thank you very much for your attention. Next thing I'll do will be looking at some of the concepts of software and applications. I'll touch a bit on communications along the pathway. Thank you very much.